Let's move to problem number 2, which is a problem related to kinematics. An object is moving with uniform acceleration a 3 meters per second squared. Determine the functions for a velocity, and it gives you some initial condition v0 10 meters per second, and for b displacement is asked, displacement s in meters, and it gives you one initial condition where s for t equals 0 is 5 meters. C, calculate the values of v and s for t equals 2 seconds and t equals 5 seconds. So let's start with the first one. We know that the acceleration is equal to 3, is constant function. The acceleration is the derivative of the velocity with respect to time. That's gonna be 3. So from here we have dv equal 3 dt. So basically we have to integrate this, integrate both sides. Then we have v equals 3 times the integral of dt is just t. So it's going to be 3t plus c1, a constant of integration. V of t as a function of time is 3t plus c1. We have an initial condition for t equals 0. We plug here t equals 0. And we have v0 equals 3 times 0 plus c1. This, of course, 3 times 0 is going to be 0. And we have v0 equals c1. v0 equals c1. But v0 is equal to 10. So from here we have that c1 equals 10. Now we go back here to the general formula, this one, let's go to that one, and we plug c1 equals 10 to get the final expression for my function v of t. That's going to be 3t plus 10. So it's going to be a linear expression, a linear function. It's going to be a linear function. That's for the first question. Now to find the displacement, we have that v of t equals 3t plus 10. We have to integrate this, integrate v, integrate both sides to find the displacement. So s of t is going to be the integral of that, and the integral of 3t plus 10 dt plus a constant of integration c2. Integral 3t dt plus integral of 10 dt plus c2. It's going to be 3 times the integral dt plus 10 times the integral dt plus c2. The integral of dt is going to be just t. Here is integral t. So that's going to be t squared over 2 plus 10 times the integral of dt is going to be t plus c2. Okay? So my function is going to be s of t. The displacement function is going to be 3/2 t squared plus 10t plus c2. That's going to be my displacement. And now I have to use the initial condition that s0 equals 5. So I put t equals 0 here, and I have s0 is 3 over 2 times 0 squared plus 10 times 0 plus c2. S0 is 5, and that is equal to, this is going to vanish, this term is going to vanish, so C2 at the end of the day is going to be 5. Now I go back here to my function and I plug C2 equals 5, so what I get at the end of the day is S of t is 3 over 2 times t squared plus 10t plus 5. And that is the expression for the displacement as a function of t. Now let's go to do the C part of this problem. Let me rewrite the functions. V of t equals 3t plus 10, and S of t is 3/2 t squared plus 10t plus 5, and I want to evaluate these functions for t equals 2 seconds and t equals 5 seconds. So for t equals 2 seconds, I have v of 2, 3 times 2 plus 10, so that's gonna be 16 meter per second, and S of t, I plug t equals 2 here, it's gonna be 3/2 times 2 squared plus 10 times 2 plus 5. 3 over 2 times 4 plus 20 plus 5. That's gonna be 6 plus 20 plus 5. 26 plus 5. So that's gonna be 31 meters. Okay? So let's put everything inside the box. V2 equals 16 meter per second, and S2 equals 31 meters. Okay. Now let's evaluate for t equals 5. So we have V of t equals 3t plus 10, and S of t 3/2 times t squared plus 10t plus 5. So for t equals 5, V of 5 is going to be, we do substitution, 3 times 5 plus 10, that's going to be 25 meter per second. And to find the displacement, S of 5 is going to be 3/2 times 5 squared plus 10 times 5 plus 5. It's going to be 25 times 1.5 plus 55. So that's gonna be 92.5 meters. So from here S5 is going to be 92.5 meters. And V5 is going to be 25 meter per second. And we are pretty much done for this part. It was a classical kinematics problem where you have the acceleration as a function of t, is a constant, and then you integrate to find to find the velocity, and then you integrate to find the displacement. Okay, all done here.